Hey everybody, this is Moballer12 here to help quench that knowledge thirst. For this video, I'll be specifically focusing on ionic and molecular compounds. Okay. Before I get into it, I want to give you guys a quick little update. Again, Facebook fan page, link in the description box below. Check that out. Go to that page, like it, show your love and support for your boy. Also, I discussed in two videos. I believe the videos are called Quickie Update and also Carboxylic Acid Synthesis. I talked about this new series. If you don't know what I'm talking about when I say new series, check out my Quickie Update because I go into more detail about that. So in the Quickie Update, I talked about how I was on the fence about the new series. I'm really starting to consider about going forward with the new series and pushing forth with it. So what I want you guys to do is go to my Facebook fan page, give me some suggestions, give me some advice as to what the name of the series should be. Again, I'm a little bit on the fence, a little bit. I still have my reservation, but I'm starting to come through and actually go forward with the new series. So what I want you guys to do is give me some advice, tips, suggestions as far as what the name should be. Look forward to my Monday video where I talk about acid derivatives, where I'll give a more definitive answer. Okay, that video should be uploaded on Monday. Okay. I think that pretty much covers the update. So let's move into ionic and molecular compounds. This video, heads up, might be a little bit long-winded, but that's the nature of most of my videos. But the reason why I say this right now is because this topic is extremely important. This is the basis for a lot of chemistry. Okay, there's no way of bypassing it. You need to understand it. I can't express how important this is. Sure, I could have made a 10-minute video discussing how to make an ionic compound, but that wouldn't have done any good for you guys. So that's why I'm going to go into the whole process of ionic and molecular compounds. Okay, so bear with me. So before we get into ionic compounds, we need to understand how do we form ions, and before we learn how to make ions, we need to understand the periodic table because that tells you a lot of information about it. So here we have the periodic table, and we're basically going to dissect the periodic table and just understand the different parts of it. Okay. So in the far left, so let's start with this overview of the periodic table. The far left, you have these two columns. They're composed of they make up the metal section. This 4x10 block right here, along with this 2 by however many. I think that's a 2 by 12 or 14. I'm not too sure. That block right there on the bottom also composes this combination right here. It composes transition metal elements. Okay, and then we have the staircase right here. This 2, 4, 6, 7, 8, which composes the metalloids, and then we have the non-metals. Okay, on this section right here. We can further break this down into smaller components. So the column on the right hand side right here is known as your noble gases. This is extremely important when we talk about ionic compounds. So this is your noble gases. Then we have your this column right here is known as your halogens, and this column right here is known as your chalcogens. Let's move to this side. This group right here, this column right here is known as your, let's see, alkali metals. This one is your alkaline earth metals. This one is known as your lanthanides. This is known as your actinides. Okay, so Los Angeles, LA, lanthanides, actinides. Nice little mnemonic. Anything else that I could say about these? Well, I could talk a little bit about the properties of these sections. Again, metals, they're conductive of both heat and electricity. They're malleable. You could bend them and shape them into certain forms. Typically, they're all solid and they're a normal state with the exception of mercury. Mercury is a liquid in this natural state. Metalloids have a combination of both non-metal and metal properties. Non-metals are not really that conductive of both heat and electricity. Let's see, anything else? Some of them are pretty poisonous. Some of the non-metals, they're mostly gaseous in their elemental state. These guys right here, specifically the noble gases, are extremely stable and they're extremely inert. They're not really reactive. Okay, so and that's what makes them so important when we talk about ionic compounds. So that's a little quick overview of the periodic table. So now let's divert our attention to this board I have here. Okay, and some of the things that I've written on here. Okay, we're going to get to this image down here a little bit later, but let's focus on the top portion of the board. Top portion of the board, I say atoms. This is the first most important thing you need to internalize, okay, and memorize. Atoms will gain or lose electrons to have equal number of electrons like noble gases. Again, I'll repeat that again. Atoms will gain or lose electrons to have equal number of electrons like noble gases. Now let's look at the periodic table again. Again, I can't express how important that is. Atoms will gain or lose electrons to have equal number of electrons like noble gases. So we're going to focus on this side of the periodic table. Okay, again, this is the fourth time repeating it. That's why it's so you can see how important it is. Atoms will gain or lose electrons to have equal number of electrons like noble gases. Okay? So, now we're focusing on ions. How do we form ions? And that's the first most important thing you need to internalize. Just quick little heads up, ions are basically atoms that have charge. If it has a positive charge, it's known as a cation. If it's a negatively charged atom, it's an anion. Okay, so that's what ions are. Okay. So again, for the fifth time, atoms will gain or lose electrons to have equal number of electrons like noble gases. In its elemental state, like I've been referring to in a bunch of videos, in its elemental state, that is basically the state at which it has no charge. Every single element had this number up top. So for example, for fluorine, it's 9. Generally speaking, the number up top refers to the atomic number, the number of protons. But if we're referring to its elemental state where it has no charge, if you have 9 protons, which are positively charged particles, you need to have 9 electrons. That's when we're referring to the elemental state. So this number could both refer to the number of protons and electrons when we're dealing with the elemental state. Key thing to realize. Okay. That's again, elemental state, that's when it's neutral. And it applies to every single element on the periodic table. So I said the atoms, sixth time now, atoms will gain or lose electrons to have equal number of electrons like noble gases. So that means that, for example, let's look at fluorine. Fluorine has 9 electrons, okay? It wants to look like a noble gas because noble gases, like I said earlier when I was discussing the properties, are extremely stable. They're extremely inert. They're not really reactive, okay? Everybody wants stability in their lives, okay? Think of this section of the periodic table, this column right here, as the kings and queens of the chemical world. Everybody else on the periodic table are the peasants and middle class. They want to emulate the kings and queens. They want to copy the kings and queens. And how they copy the kings and queens of the periodic table is by having a similar electron count. That was my first statement that I kept repeating 6 times. Okay, so they'll gain or lose electrons to have a similar electron count like the noble gases. So in this case, fluorine had 9 protons, 9 electrons. The number of protons is not that significant right now, but the number of electrons is more important, okay? Because that's what helps it reach stability, okay? Everybody wants stability in their lives. So fluorine, for example, has 9 electrons. It could gain 1 electron to have 10 electrons like neon, or it could lose 7 electrons to look like helium, or it could gain 9 electrons to look like argon, or it could gain 27 electrons to look like krypton, or it could gain 45 electrons to look like xenon, or it could gain 76 electrons to look like radon. Now here's the problem. We don't know which way it's going to go. Is it going to gain that many electrons? Is it going to lose that many electrons? How do we know whether it's going to gain 1 or gain 9 or lose 7? Well, this leads perfectly into the next statement I want you guys to internalize, okay? The second statement is atoms will minimize the gain or hold on, what did I say? I got lost. Okay, atoms will minimize the gain or loss of electrons to reach noble gas electron configuration in a fashion known as the path of least resistance. Okay, I just came up with that because it kind of fit in nicely into this topic. So path of least resistance, that's a key thing to realize. Minimize the gain or loss of electrons, another important part of that statement. That's key right there. That's your bread and butter. So in the path of least resistance, let's look at this right here, and I'll give you guys another analogy. Path of least resistance is the most key thing to realize, okay? So for example, fluorine, like I said, could gain 1 electron to look like neon. Let me zoom in just a little bit more. It could gain 1 electron to look like neon, or it could gain 9 electrons to look like argon, or it could lose 7 electrons to look like helium. That path is extremely hard. Losing 7 is extremely hard, and you'll learn about it later on when we talk about ionization in future videos. Gaining electrons is extremely hard. Gaining that many electrons, basically gaining 9 electrons is extremely hard. Gaining 27 electrons is extremely hard. The path of least resistance, again, the second statement was the path of least resistance, and also minimize the gain or loss of electrons. The most minimal amount of electrons you could gain or lose in this case will be gaining 1 electron. Okay, so fluorine is going to gain 1 electron to look like neon. Let's look at another case. Chlorine, 17 protons, 17 electrons. It could gain 1 to look like argon, or it could lose 7 to look like neon, or it could lose 15 to look like helium, or gain 19 to look like krypton. Well, in the path of least resistance, okay, it wants to look like one of these noble gases, but in the fashion of path of least resistance, it's going to look like argon, because all it has to do is gain 1, path of least resistance. It gains or loses the least amount. In this case, it will gain the least amount. Okay, so I'll give you guys another quick analogy. There's an opening, okay, for a big time company. Okay, there's a CEO position opening, and the job description basically says you could have 2 or 4 years of education in order to get this position. Okay, and you'll start off making about 500K a year. Okay, so again, 2 years or 4 years of education in a specific field. Now, for the most part, given that type of opportunity, 99%, I can't make up an exact statistic, but we'll say for the most part, a majority of the people will go ahead with the path of least resistance and go get the 2 years of education and go pursue becoming the CEO of that company and start making those big bucks. Okay, 500K is still very low for becoming a CEO, but still, just for this analogy, it will make, for the most part, most people will go ahead and pursue the 2 years education and then become a CEO. There will be some people, very few, that might just go and do the 4-year program and then pursue becoming a CEO for that company, but the likeliness of them doing that, even still, is very low. Okay, but those who do will do because they love education, because they love learning so much. Okay, but nonetheless, path of least resistance. You're not going to spend 4 years trying to make the same amount of money when you can make that much money going 2 years of schooling. Okay, so that's the path of least resistance, and that same thing applies in the chemical world, where atoms will gain or lose electrons to minimize that gain or loss. Okay, so let's look at, for example, oxygen. Oxygen has 8 electrons, 8 protons in its elemental state. It could gain 2 electrons to look like neon, or it could gain 10 electrons to look like argon, or it could lose 6 electrons to look like helium. Well, in this case, path of least resistance, it will gain 2. Let's look at this side. Lithium. Let me zoom out a little bit so you guys can see this guy. Okay. Lithium, Li right there, has 3 protons, 3 electrons. It could gain 7 to look like neon. Okay, or it could lose 1 to look like helium. Okay, helium's up top right there. Or it could gain, let's see, or lithium could gain 15 to look like argon. In the path of least resistance, it will lose, in this case, 1 electron to look like helium. Okay, regardless if it's a gain or loss of electrons, you're gonna go in the path of least resistance. That means if you can lose less electrons than gaining electrons, you're going to go in that fashion. Okay? If you could gain less electrons than lose electrons, you're going to go in that fashion. So it applies both vice versa. Okay? But there's a nice little trend now, and that trend is that non-metals will typically gain electrons. Metals will typically lose electrons. Key thing to memorize. Okay? So now let's divert our attention to this drawing I have here. Okay, and this is doing the same kind of explanation I did before, but now we have a little drawing to back it up. Okay, so here we have, that's fluorine right there. Okay, here we have a very generic looking atomic structure of fluorine. Okay, right here, let me zoom in on this portion of the board so you guys can see it. Right here we have 9+. Okay, well, in the core there's 9 protons, and you can look at that Look at the periodic table to decipher that information by looking at that number above the element symbol. The number of neutrons doesn't really matter. So there's 9 protons, which basically has a positive 9 charge, and I just put the charge there. Surrounding it in its elemental state are electrons, and you will have effectively 9 electrons. The sum of both of the positives and the negatives will equal 0. So 9 protons, which are positively charged things, and 9 electrons, which are negatively charged things, will sum out to 0. Now, like as we discussed and looked at the periodic table, fluorine will, let's zoom in a little bit, fluorine will gain 1 electron in the fashion of path of least resistance to emulate the noble gases. Again, they want to emulate the kings, so it'll gain 1 electron. So that's what we did here. So now, surrounding the nucleus, instead of having 9 electrons, we have 10 electrons. We still have 9 protons here, okay, but we have 10 electrons now around here. So again, we will do the same little calculation. We have negative 10 things. So we have not negative 10 things. We have 10 things that bear a negative 10 charge, and we have 9 things that bear a positive 9 charge, referring to the protons and electrons. Get the sum of those two, we'll get a negative 1. So by gaining 1 electron, in the case of fluorine, fluorine gets a negative 1 charge, and it becomes this ion known as fluoride. So just some key thing to recognize, that whenever you go from its elemental state to its ionic state, the name changes. It goes from fluorine to fluoride. It could go chlorine to chloride. It will go oxygen to oxide. It will go sulfur to sulfide, bromine to bromide, and carbon to carbide, stuff to that effect. Okay, nitrogen to nitride when it becomes an ion. It's a key little thing to memorize. The next thing you need to look at is this little drawing on the bottom. I did one for the nonmetals and I did one for the metals. So here we have sodium. It has 11 protons, which carry a positive 11 charge. It has neutrons, not really significant in this case. Surrounding it are 11 electrons. Each one of them have a negative 1 charge. 11 total will equal a negative 11. In its elemental state, sodium has a 0 charge. Now if we looked at sodium, it could gain 7 to look like argon, but like I said, metals tend to lose, so sodium will lose 1 electron to look like neon and have 10 electrons, like neon. So in this case, now there's 10 electrons surrounding it, so you have 10 negatively charged particles surrounding the nucleus. So let me so you have a negative 10 plus 11, it gives a positive charge, so it'll be sodium plus 1. And when I was talking about the naming structure, the naming, you know how it goes fluorine to fluoride, chlorine to chloride, bromine to bromide, so on and so forth. That only applies to non-metals. Metals will not change their name. It won't be sodium to sodide or something like that. It will always remain sodium, both in its elemental state and in its ionic state. The only thing you need to realize that for non-metals, when it goes to become an ion, the name changes, and I'll talk about that a little more in the future. So stay tuned to the second part where I go into a little bit more details.